Late September 1944. Kummersdorf Proving Ground, Brandenburg, Germany. The captured M4A3 Sherman tank rolled into position on the test track, its hull bearing fresh German tactical markings over the faded white star of the United States Army. Hauptmann Klaus Becker of the Wehrmacht's weapons testing office climbed into the turret, settling into the gunner's position while his assistant adjusted the optical rangefinder outside. They had tested dozens of captured enemy vehicles at this facility over the past 3 years, but this particular Sherman, serial number USA 3089547, would force German tank designers to confront a technological reality they had dismissed as tactically insignificant. The test protocol was straightforward: drive the tank at combat speed across uneven terrain while engaging simulated targets at ranges between 400 and 800 meters. German doctrine emphasized stopping to fire, a tactical principle deeply embedded in Panzer crew, training and tank design philosophy. This test would demonstrate why American tank crews could do something German tankers could not: maintain accurate fire while moving at speed across broken ground. Becker gave the signal. The Sherman lurched forward, engine roaring as the driver accelerated to 20 kilometers per hour across rutted proving ground terrain designed to replicate battlefield conditions. The hull pitched and yawed violently over the uneven surface. Inside the turret, Becker placed his eye against the gunner's sight and aligned the reticle on a target silhouette positioned 600 meters downrange. Then he engaged the gyroscopic stabilizer. The gun tube moved independently of the hull's violent motion, maintaining its precise elevation as if suspended by invisible forces, while the tank beneath it bucked and swayed over rough terrain. Becker pressed the firing button. The 75mm gun fired. The target silhouette collapsed, struck cleanly despite the Sherman's movement and the challenging range. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Becker climbed out of the turret 20 minutes later, after conducting multiple engagement sequences against varied targets while the Sherman maintained combat speed. He found his superior officer, Oberst Friedrich Halder, waiting beside the observation post with arms crossed and expression grim. Both men understood what they had just witnessed. The Americans had solved a fundamental problem in armored warfare that German engineers had considered either impossible or tactically irrelevant. The Sherman's gyrostabilizer permitted accurate fire while moving, transforming tank gunnery from a static artillery duel into a dynamic engagement where mobility became a weapon rather than a liability. This single technical capability, dismissed by German tank designers as unnecessarily complex and prohibitively expensive, had rendered German tactical doctrine obsolete in the mobile warfare scenarios both armies would face during the coming months of fighting across France and into Germany itself. The implications were devastating. Every Panther, Tiger, and Panzer IV in Wehrmacht service required stopping completely to engage targets accurately. American Shermans could fire effectively while maneuvering at combat speed. In tank versus tank combat, the side that fires accurately first usually wins the engagement. The mathematics of that tactical reality were simple and brutal. American tank crews could begin engaging while closing range or while withdrawing from unfavorable positions. German tank crews had to become stationary targets. The Americans possessed a decisive advantage that no amount of superior armor, thickness, or gun penetration could overcome if German crews were destroyed before their weapons could be brought to bear effectively. This realization, documented in technical reports filed at Kummersdorf during autumn 1944, came far too late to influence German tank design or to alter tactical outcomes in the war's final year. But it represented a profound admission by Wehrmacht technical officers that American industrial engineering had achieved practical battlefield capabilities German designers had never seriously attempted. The gyrostabilizer was not science fiction or theoretical technology. It was production reality installed in thousands of American tanks. The story of how one mechanical system changed the mathematics of armored combat begins not at Kummersdorf in 1944, but years earlier in American industrial research facilities where engineers applied practical problem-solving to identified tactical deficiencies without regard for whether the solution seemed theoretically elegant or conventionally achievable. The United States Army had recognized the problem of firing while moving as early as the 1920s. Cavalry branch officers, observing mechanized warfare exercises, noted that armored vehicles sacrificed their primary advantage of mobility whenever they stopped to fire weapons. Stationary tanks became easy targets for enemy artillery, anti-tank guns, and opposing armor. Mobile tanks that could not fire accurately were merely fast-moving targets with no offensive capability. The tactical dilemma seemed insoluble given the technology available during the interwar period. Gun stabilization required precise mechanical control systems, gyroscopic reference platforms, and hydraulic or electrical actuators capable of moving heavy gun tubes with sufficient speed and accuracy to compensate for vehicle motion. All of this had to function reliably under combat conditions, including shock, vibration, temperature extremes, and the electrical interference common in armored vehicles. Most military designers worldwide considered the problem too difficult to justify the development. Investment. British engineers made preliminary attempts at stabilization during the 1930s, developing systems that provided limited vertical stabilization for some tank guns. These early systems proved mechanically complex, frequently unreliable, and offered insufficient performance to justify their installation in production vehicles. The British approach demonstrated the concept's feasibility, but not its practical utility. American engineers at the Westinghouse Electric Company took a different approach. Rather than attempting perfect stabilization through pure mechanical means, they developed a gyroscopically referenced hydraulic system that provided adequate stabilization for combat purposes while remaining simple enough for reliable mass production and field maintenance. The key insight was accepting that perfect stabilization was unnecessary. The gun needed sufficient stability to keep the target within the gunner's field of view while moving, allowing the gunner to make final aiming corrections and fire when the sight picture was adequate. The Westinghouse design used a spinning gyroscope mounted rigidly to the gun tube to provide an inertial reference independent of hull motion. When the hull pitched or rolled, the gyroscope maintained its orientation in space. Electrical pickoffs detected any deviation between the gyroscope's orientation and the gun tube's actual position. These error signals fed into a control system that commanded hydraulic actuators to rotate the gun tube in elevation, driving the error toward zero and maintaining the tube's alignment with the gyroscope's reference. The system operated continuously while activated, making constant small corrections to compensate for hull motion. It could not eliminate all movement. The gun tube still oscillated slightly around the target's position, but it reduced violent motion to manageable tremors that skilled gunners could work through, firing during brief moments when the sight picture was acceptable. Development work proceeded through the late 1930s, with prototype systems tested on various tank chassis. By 1941, Westinghouse had refined the design sufficiently for production consideration. The United States Army Ordnance Department, convinced of the system's tactical value through testing results, mandated stabilizer installation in the new M4 medium tank, then entering production. This decision was remarkable for several reasons. The stabilizer added complexity, weight, and cost to every Sherman produced. It required specialized maintenance and electrical power generation beyond what simple tanks needed. Most significantly, it represented a substantial technical risk during the rush to mass production. If the stabilizers proved unreliable in field service, thousands of tanks would have critical systems requiring constant repair. American industrial planners accepted these risks because they understood that tactical advantage justified technical complexity if the system could be manufactured reliably at scale. The United States possessed the industrial infrastructure, skilled workforce, and manufacturing expertise to produce complex electromechanical systems in quantity while maintaining quality control. Germany did not, particularly after 1943 when strategic bombing and resource shortages increasingly constrained German manufacturing capabilities. The Sherman's gyrostabilizer stabilized the gun in the vertical plane only. The turret itself was not stabilized in traverse, meaning the gun could still swing horizontally with hull motion. Gunners had to track targets manually in azimuth, while the stabilizer maintained elevation. This limitation seemed acceptable given the alternative of no stabilization whatsoever, and the technical challenges of adding traverse stabilization to turrets weighing several tons. Production Shermans began reaching United States Army units in late 1942. Initial crew reactions to the stabilizer were mixed. The system required electrical power, making it unavailable if the tank's electrical system was damaged or if generators failed. Some crews found the stabilizer's constant corrections distracting, particularly gunners trained on unstabilized weapons who had developed techniques for timing their shots between hull motions. Tank commanders had to decide whether to train crews to use the stabilizer aggressively, firing while moving, or to employ it primarily as a rapid target acquisition aid, allowing gunners to get on target quickly after the tank stopped. Different units developed different tactical approaches based on their commanders' preferences, crew training standards, and combat experiences. The system's true tactical value became apparent during the North African campaign in 1942 and 1943, where mobile engagements across open desert terrain favored tanks that could engage while maneuvering. American tank crews discovered they could fire effectively at ranges beyond 800 meters while moving at 15 to 20 kilometers per hour, something their opponents with unstabilized guns could not achieve. British tankers, observing American methods, began requesting Sherman tanks specifically because of the stabilizer's capability. British tank doctrine had emphasized static, hull-down defensive positions where stabilization offered minimal advantage. But North African combat forced tactical adaptation. Mobility and rapid fire during movement proved more valuable than armor thickness or gun penetration in the fluid battles across desert terrain. The Germans captured their first intact operational Shermans during fighting in Tunisia during early 1943. Initial technical evaluations focused on armor thickness, gun penetration, automotive reliability, and overall design philosophy. These assessments, conducted at Kummersdorf and other testing facilities, revealed American advantages in manufacturing sophistication and automotive engineering that deeply troubled German technical officers. But the stabilizer system received surprisingly little attention in early German reports. Evaluators noted its presence, described its mechanical configuration, and acknowledged that it functioned as designed. They did not initially recognize its tactical significance or understand how American crews were employing it in combat. This oversight reflected German tactical doctrine and training philosophy. Panzer Doctrine emphasized accurate long-range gunnery from carefully selected firing positions, with tanks stopping completely, identifying targets precisely, and engaging with aimed shots that maximized the probability of first-round hits at maximum effective range. This approach made perfect sense, given German gun advantages. The Panther's 75mm K-42 liters, 70 gun, and the Tiger's 88mm K-36 liters, 56 gun possessed superior penetration, compared to the Sherman's 75mm M3 gun, particularly at ranges beyond 1,000 meters. German doctrine sought to exploit this advantage by engaging American tanks at ranges where German guns could penetrate Sherman armor, but American guns could not penetrate German armor effectively. From this doctrinal perspective, firing while moving seemed tactically pointless. Why sacrifice accuracy by firing on the move when doctrine called for long-range precision fire from static positions that maximized German gunnery advantages? The stabilizer appeared to be an expensive mechanical complexity that addressed a problem German doctrine defined as non-existent. This assessment persisted through much of 1943 and into early 1944. German technical reports acknowledged the stabilizer, but classified it as a curious American engineering excess rather than a significant tactical capability. Wehrmacht training materials did not emphasize the stabilizer as a threat requiring tactical countermeasures. Panzer crews received no specific instruction on how to counter an enemy that could engage accurately while moving. The tactical reality of combat in France after D-Day in June 1944 forced a dramatic reassessment. The bocage terrain of Normandy, with its small fields enclosed by thick hedgerows and limited sightlines, created combat conditions completely unlike the open terrain of North Africa or the Russian steppes. Tank engagements occurred at close range, often under 500 meters, with limited opportunities for the long-range precision gunnery that German doctrine assumed. In these close-range environments, Mobility and rapid engagement became more valuable than armor thickness or gun penetration. The side that fired first usually won, regardless of whether their gun could penetrate the opponent's armor at that specific range. Even non-penetrating hits could damage optics, disable weapons, or force crews to button up, degrading their combat effectiveness. American tank crews, well-trained in stabilizer employment, could acquire targets quickly while moving, engage effectively at combat ranges while maintaining movement, and execute shoot-and-scoot tactics that denied German gunners stationary targets. German Panzer crews, trained to stop before firing, became predictable and vulnerable. The tactical pattern repeated across hundreds of engagements during summer and autumn 1944. A Sherman platoon would advance through bocage terrain, maintaining movement. German tanks would stop to engage, following Doctrine. The Shermans would fire while still moving, often achieving hits before the German crews could complete their aiming sequence. Even if the Sherman's 75mm rounds failed to penetrate frontal armor at longer ranges, the impacts disrupted German aim, and the Sherman's continued movement complicated German fire solutions. German crews found themselves forced into a losing tactical equation: stop to fire accurately per Doctrine, and become a stationary target for an enemy who could engage while moving, or attempt to fire while moving using unstabilized guns and sacrifice accuracy against an enemy whose stabilized guns maintained reasonable accuracy during movement. Wehrmacht, after action reports from France, began noting this tactical dilemma with increasing frequency and concern. Company commanders reported that American tanks were engaging aggressively while German tanks were being destroyed before they could return effective fire. Battalion and regimental after-action assessments noted declining kill ratios and rising German tank losses that could not be explained solely by American numerical superiority or air support. The reports reached Wehrmacht technical branches responsible for tank development and tactical doctrine revision. In autumn 1944, Wehrmacht Weapons Testing Office issued orders for comprehensive re-evaluation of captured Sherman tanks, with specific emphasis on the gyrostabilizer system and its tactical implications. This leads directly to the tests conducted at Kummersdorf in September and October 1944, where German technical officers systematically explored the stabilizer's capabilities under controlled conditions and reached conclusions they had resisted for over a year. The admission was painful, but unavoidable. The Americans had developed and deployed a technology that fundamentally altered the tactical mathematics of tank combat in ways German designers had not anticipated and could not easily counter. Hauptmann Becker's technical report, filed in October 1944, documented the stabilizer's performance with Germanic thoroughness. He measured accuracy while moving at various speeds, compared hit probabilities between stabilized and unstabilized fire, calculated the time advantage gained by engaging while closing range, and analyzed the tactical play and stem, scenarios where stabilization provided decisive advantage versus scenarios where it offered minimal benefit. His conclusions were unambiguous. At ranges below 800 meters, against targets of opportunity, in terrain restricting maneuver and limiting sight lines, the gyrostabilizer provided American tank crews with a significant first-shot advantage that outweighed German advantages in armor protection and gun penetration. The stabilizer effectively neutralized German tactical doctrine by allowing American crews to engage before German crews completed their aiming sequences. Becker noted that German tank gunnery training emphasized precision and patience. Gunners were taught to identify targets carefully, range them accurately, select ammunition types appropriately, aim precisely, and fire when confident of a hit. This methodical approach maximized hit probability and conserved ammunition but required time. American gunnery training, by contrast, emphasized rapid engagement, volume of fire. Gunners were taught to acquire targets quickly, achieve adequate aim using the stabilizer, and engage rapidly while moving. This aggressive approach sacrificed some precision, but gained speed and maintained momentum. In close-range engagements where both sides could penetrate each other's armor, speed mattered more than precision. The implications extended beyond individual crew training to fundamental questions of tank design philosophy and industrial capacity. Gyrostabilizers required substantial engineering investment to develop, sophisticated manufacturing capabilities to produce, and electrical systems to power. They added cost, complexity, and potential maintenance burdens to every tank produced. German tank designers had rejected this path consciously, choosing instead to invest engineering effort and manufacturing resources into thicker armor, more powerful guns, and sophisticated fire control optics. These choices reflected German military philosophy that emphasized technical quality and individual vehicle superiority over quantity production and system-level integration. American designers made opposite choices, accepting reduced armor protection and adequate, rather than optimal, gun penetration in exchange for mechanical reliability, ease of manufacture, and tactical capabilities like stabilized fire that enhanced overall combat effectiveness through better system integration rather than superior individual components. Neither approach was objectively right or wrong in abstract theoretical terms. The question was, which philosophy better matched industrial reality, tactical requirements, and strategic circumstances? By late 1944, the answer was becoming devastatingly clear. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical architecture of the Westinghouse stabilizer system reflected decades of American placis, industrial experience in precision, mechanical control systems, electrical engineering, and hydraulic power transmission. Understanding how the system functioned reveals why German engineers found replicating it so difficult, despite possessing theoretical knowledge of gyroscopic stabilization principles. The heart of the system was a rate gyroscope mounted rigidly to the gun tube through a mechanical linkage. This gyroscope, spinning at approximately 20,000 revolutions per minute, established an inertial reference frame independent of the tank's motion. When the hull pitched upward over terrain irregularities, the gyroscope maintained its orientation in space, while the gun tube attempted to follow the hull's motion. This angular displacement between the gyroscope and the gun tube generated an electrical error signal proportional to the deviation. The error signal fed into an amplifier circuit that controlled a hydraulic servo valve. The servo valve directed pressurized, hydraulic fluid to a cylinder connected to the gun's elevation mechanism, driving the gun tube back toward alignment with the gyroscope's reference orientation. The system operated as a closed feedback loop, continuously sensing deviation and generating corrective motion. Response time was critical. If the corrections lagged too far behind hull motion, the gun would oscillate wildly around the target rather than maintaining steady aim. If corrections were too aggressive, the system would become unstable, amplifying rather than damping motion. Westinghouse engineers tuned the system's response characteristics through careful selection of feedback gains, hydraulic flow rates, and damping coefficients. The result was a stabilizer that responded quickly enough to track hull motion, but not so aggressively that it became unstable or wore out mechanical components through excessive movement. Power for the system came from the Sherman's electrical system. A motor generator set provided the precise voltage and frequency required by the gyroscope motor and control circuits. Hydraulic pressure came from a dedicated pump driven by the tank's engine through power takeoff. Both systems had to function reliably under combat conditions including shock, vibration, temperature extremes, and electrical interference from the radio equipment and ignition system. The complexity was substantial but manageable given American manufacturing capabilities. Westinghouse produced the gyroscope assemblies and control electronics. Other contractors manufactured hydraulic components. Final assembly occurred at the tank production facilities, where workers installed and tested the complete system as part of the normal production process. Quality control was critical. A stabilizer that failed in combat left the crew with an unstabilized gun, eliminating their tactical advantage. American production facilities implemented rigorous testing protocols. Every stabilizer underwent functional testing before the tank left the factory. Maintenance manuals provided detailed troubleshooting procedures, and spare parts were integrated into the logistics system supporting Sherman operations. This level of system integration and production sophistication reflected American industrial maturity developed through decades of manufacturing complex consumer products like automobiles, aircraft, and electrical appliances. The United States possessed the machine tools, skilled workforce, quality control systems, and engineering expertise necessary to produce electromechanical systems reliably at scale. Germany possessed brilliant scientists and talented engineers, but German industry lacked the manufacturing depth and workforce training to replicate American production methods, particularly after 1942, when strategic bombing began disrupting production and skilled workers were drafted into military service in increasing numbers. German technical officers examining captured Sherman stabilizers at Kummersdorf understood the system's operating principles without difficulty. They could measure performance, analyze the control architecture, and comprehend the engineering solutions Westinghouse had implemented. What they could not do was replicate the system in German tanks within any realistic time frame given Germany's deteriorating industrial situation. Several factors made stabilizer adoption impossible for Germany by late 1944. First, the engineering development work required months or years. Adapting stabilization to existing German tank designs would require extensive redesign of turret structures, gun mounts, and electrical systems. Developing a new stabilizer optimized for German guns and turret configurations would require even longer. Second, production tooling and manufacturing processes would need complete revision. German tank factories were optimized for producing unstabilized guns using established methods. Introducing stabilizers meant retooling production lines, training workers in new assembly procedures, and establishing quality control systems for unfamiliar technology. All of this required time and resources Germany did not possess. Third, the electrical and hydraulic support systems would need upgrading. German tanks generally possessed less sophisticated electrical systems than Sherman's. Installing stabilizers would require more powerful generators, upgraded wiring, and additional hydraulic pumps. These modifications cascaded through the entire vehicle design, adding weight, complexity, and cost. Fourth, maintenance and logistics systems would need expansion. Stabilizers required specialized repair procedures and spare parts. German logistics were already strained, supporting existing equipment. Adding complex new systems would further burden an infrastructure collapsing under Allied bombing and fuel shortages. Finally, and most fundamentally, Germany's strategic situation by late 1944 made major tank development programs pointless. The Wehrmacht was fighting a desperate defensive war on multiple fronts against enemies with overwhelming material superiority. Introducing new technology into production could not alter strategic outcomes determined by industrial capacity, resource availability, and military manpower. German engineers did attempt preliminary stabilizer development work during 1944. Surviving documents indicate that several firms explored gyroscopic stabilization concepts for tank guns. These projects remained purely experimental, never advancing beyond prototype testing. None reached production consideration before the war's end. The tactical implications of the stabilizer advantage played out across hundreds of engagements during the final year of war in Europe. Specific examples from combat records illustrate how the technology translated into battlefield results. December 5, 1944. Near Echternach, Luxembourg. Company B of the 10th Armoured Division's 21st Tank Battalion engaged elements of the German 12th Volksgrenadier Division during German counterattacks preceding the Battle of the Bulge. The engagement occurred in rolling terrain with scattered woods and limited visibility due to morning fog. A platoon of 4 M4A3 Shermans, commanded by First Lieutenant Robert Hammond, moved through a shallow valley when German anti-tank guns opened fire from concealed positions on the ridgeline. The lead Sherman took a hit that damaged its tracks, but did not penetrate the hull. Hammond's tank, second in column, immediately returned fire while still moving, using the stabilizer to maintain aim despite the rough terrain and evasive maneuvering. The 75mm gun engaged the German position at approximately 600 meters range. Hammond's gunner, Sergeant James Mitchell, fired 3 rounds in rapid succession, while the Sherman continued moving at 15 kilometers per hour. The second and third rounds struck the German gun position, destroying the anti-tank weapon and killing or wounding the crew. The engagement lasted perhaps 20 seconds from the German gun's first shot to its destruction. The stabilizer allowed Mitchell to acquire the target quickly despite hull motion, achieve adequate aim without stopping, and maintain fire while Hammond maneuvered the tank evasively. A German Panzer IV in the same situation would have needed to stop completely to return accurate fire, losing precious seconds and becoming a stationary target. Similar engagements occurred repeatedly during the Ardennes Offensive in December 1944 and January 1945. German armoured units attacking through forested terrain in winter conditions encountered American tank units that could engage effectively while withdrawing or repositioning. The tactical flexibility provided by stabilized fire helped offset German advantages in armour protection and gun penetration. March 10, 1945. Crossing the Rhine River near Remagen, Germany. The 9th Armoured Division's Combat Command B exploited the captured Ludendorff Bridge, pushing armoured columns across the Rhine before German forces could organise effective resistance. Tank platoons from the 14th Tank Battalion engaged German defenders in the hills east of the river. Technical Sergeant William Crawford commanded a Sherman tank supporting infantry clearing German positions from industrial buildings. His tank moved through rubble-strewn streets while engaging targets of opportunity, including machine gun nests, anti-tank weapons, and infantry strongpoints. The stabilizer permitted accurate fire against these targets, while the tank maintained movement, essential for survival in urban terrain, where stationary vehicles became easy targets for Panzerfaust anti-tank rockets. Crawford's gunner engaged 12 separate targets during a 3-hour period, firing while the tank was moving for 10 of these engagements. The after-action report noted that stabilized fire was essential for maintaining momentum during the attack, and that stopping to fire would have exposed the tank to German anti-tank weapons in nearby buildings. These tactical examples, multiplied across thousands of engagements during the war's final months, demonstrated the stabilizer's practical value in combat conditions. The technology did not guarantee victory in individual engagements. Shermans continued suffering losses to German tanks, anti-tank guns, and infantry weapons throughout the war. But the stabilizer provided a meaningful tactical advantage that improved American crew survivability and combat effectiveness in specific tactical situations. German tank crews facing Shermans in close-range engagements reported frustration at their inability to counter American tanks that fired accurately while moving. Panzer commanders noted that American tank platoons exhibited aggressive tactics, closing rapidly, while engaging, that German crews found difficult to counter using conventional doctrine. Wehrmacht tactical training bulletins issued during early 1945 attempted to address the problem through revised tactics rather than technological solutions. Crews were advised to select firing positions offering clear fields of fire at longer ranges where German gun advantages could be exploited. They were instructed to engage American tanks at maximum effective range before they could close to distances where stabilized fire provided decisive advantage. These tactical adaptations had limited effectiveness given the strategic situation. By early 1945, German armoured units were fighting defensive battles in terrain that offered few opportunities for the long-range engagements German doctrine preferred. Fuel shortages, limited mobility, reducing the ability to select advantageous firing positions. Allied air superiority made daylight movement dangerous, forcing German armour to operate at night or in poor visibility conditions that negated range advantages. The broader strategic context illuminates why the stabilizer represented more than just a tactical capability. It exemplified fundamental differences in how American and German militaries approached the industrial challenge of modern mechanized warfare. American military doctrine, shaped by industrial society and democratic political culture, emphasized mass production of adequate weapons that could be manufactured reliably, maintained by soldiers with basic training, and employed by citizen soldiers who required straightforward operating procedures. The stabilizer fit perfectly within this philosophy. It was complex enough to provide tactical advantage, but not so sophisticated that it required specialist crews or exceptional maintenance. German military doctrine, shaped by Prussian military tradition and authoritarian political culture, emphasized technical excellence, superior individual capabilities, and the assumption that highly trained specialists would operate equipment requiring exceptional skill. German tanks possessed superior armor and guns, but required skilled crews and extensive maintenance. They were built in smaller numbers to higher specifications rather than mass-produced to adequate standards. Neither approach was inherently superior in abstract terms. The question was which philosophy better matched strategic reality. By 1944, the answer was clear. American industry could produce weapons in overwhelming quantities while maintaining quality and incorporating sophisticated capabilities like gyro-stabilizers. German industry struggled to maintain production volumes while quality declined and resources grew scarce. The United States produced approximately 49,000 Sherman tanks of all variants between 1942 and 1945. Germany produced approximately 25,000 tanks of all types during the entire war, including obsolete models and tank destroyers. American production exceeded German output while also producing vast quantities of aircraft, ships, artillery, vehicles, and ammunition, supporting both American forces and Allied nations through Lend-Lease. This industrial disparity decided the war's outcome as certainly as any battle. Technology, tactics, and individual courage mattered, but industrial capacity and resource availability determined which side could sustain military operations over years of global conflict. The gyro-stabilizer symbolized American industrial advantages. It was sophisticated technology that German engineers understood but could not replicate given their resource constraints and industrial limitations. Post-war analysis by military historians and technical specialists examined the stabilizer's impact on armor warfare during World War II. Assessments varied regarding its tactical significance. Some analysts argued that the stabilizer provided a meaningful but not decisive advantage in specific circumstances. Others suggested its importance was overstated, given that most tank combat still involved static engagements where stabilization offered minimal benefit. What was not debatable was that the stabilizer represented a successful example of translating identified tactical requirements into production hardware through systematic engineering development and industrial execution. American forces identified a problem, firing accurately while moving. American industry developed a practical solution: gyroscopic stabilization. American production facilities manufactured the solution reliably at scale, installing stabilizers in thousands of tanks. This capability to move from tactical requirement through engineering development to mass production represented exactly the kind of system-level competence that decided industrial wars. It required scientific knowledge, engineering skill, manufacturing sophistication, and organizational capability functioning together effectively. German forces possessed scientific knowledge equal or superior to American knowledge in many fields. German engineers were as skilled as their American counterparts, but German industry lacked the manufacturing depth, skilled workforce, and organizational systems necessary to translate knowledge and skill into reliable mass production, while simultaneously fighting a multi-front war against better-resourced opponents. The admission by German technical officers that the Sherman stabilizer made Panzers obsolete reflected professional recognition of American advantages that German industry could not overcome. It was not an admission that German tanks were inferior in all respects. Panthers and Tigers possessed superior armor and guns compared to Shermans. In ideal circumstances, fighting at long range from prepared positions, German tanks could devastate American armor. But modern war rarely permitted ideal circumstances. Combat occurred in varied terrain, at varied ranges, under varied conditions. The side that could fight effectively across the broadest range of circumstances possessed decisive advantage. Stabilized guns extended American combat effectiveness into scenarios where German doctrine required vulnerability, specifically engaging while moving at close range in restricted terrain. The legacy of the Sherman stabilizer extended beyond World War II into post-war tank development. The principle that tanks should fire accurately while moving became standard doctrine for all modern armies. Post-war tank designs increasingly incorporated sophisticated stabilization systems, eventually adding horizontal stabilization to complement vertical stabilization and developing fire control computers that integrated stabilization with range finding, ballistic calculation, and target tracking. The British Centurion tank, entering service in 1945, featured a two-axis stabilization system that stabilized the gun in both elevation and traverse. Soviet post-war tanks incorporated increasingly sophisticated stabilizers. American tank development produced the M46 through M60 series, all featuring advanced stabilization as fundamental design requirements. Modern main battle tanks like the American M1 Abrams, German Leopard 2, and British Challenger 2 possess stabilization systems far more sophisticated than the Westinghouse gyrostabilizer in the Sherman. These modern systems use laser gyroscopes, digital control systems, and advanced hydraulic or electric drive motors to maintain incredible accuracy while moving at high speed across rough terrain. The fundamental principle, however, remains identical to what Hauptmann Becker discovered during testing at Kummersdorf in autumn 1944. Tanks that can fire accurately while moving possess tactical advantages over tanks that must stop to fire. Mobility and firepower together create combat effectiveness greater than either capability alone. 4. German tank designers and Wehrmacht tactical officers. The Sherman stabilizer represented uncomfortable proof that American industrial engineering had solved problems German designers had considered either impossible or tactically irrelevant. The admission that this technology made Panzers obsolete came too late to influence German tank development and far too late to alter strategic outcomes in a war already decisively lost. But the admission itself was significant. It represented professional recognition by technically competent officers that their assumptions had been wrong, their doctrine had been flawed, and their opponents had achieved capabilities they had dismissed. In war, recognizing uncomfortable truths is essential for learning and adaptation. By late 1944, German forces had learned what American stabilizers could do. They simply lacked the time, resources, and industrial capacity to respond effectively. The captured Sherman at Kummersdorf, with its Westinghouse stabilizer still functioning after months of testing, told a story about industrial warfare in the 20th century. Victory required not just tactical skill or technological innovation, but the industrial capacity to translate innovation into production reality at scale. The Americans possessed this capacity, the Germans did not, regardless of their scientific knowledge or engineering talent. April 1945. Kummersdorf Proving Ground, Brandenburg, Germany. Soviet forces advancing toward Berlin overran the testing facility, capturing extensive documentation of German weapons development and testing programs. Among the captured material were technical reports analyzing the Sherman stabilizer and assessing its tactical implications. Soviet engineers studied these reports with great interest. The Red Army had received thousands of Sherman tanks through Lend-Lease during the war, and Soviet tank crews had experience using the stabilizers in combat against German forces. The German technical analysis confirmed what Soviet combat experience had demonstrated, that stabilized fire provided meaningful tactical advantages in modern armored warfare. Post-war Soviet tank development incorporated increasingly sophisticated stabilization systems, building on lessons learned from both American Lend-Lease Shermans and German technical analysis of the stabilizer's capabilities. The T-54 tank, entering service in 1947, featured a two-axis stabilization system that became standard for Soviet armor throughout the Cold War. The captured Sherman that had undergone such extensive testing at Kummersdorf disappeared into Soviet hands after the war's end. Whether it was preserved, scrapped, or put to further technical use remains unknown, but its legacy persisted in the technical documentation it generated and the tactical lessons it taught. German tank designers who survived the war and continued working in military engineering during the post-war period carried forward the lessons learned from stabilizer analysis. When West Germany began developing the Leopard 1 main battle tank during the 1950s, designers insisted on sophisticated stabilization systems from the beginning. They had learned through painful experience that mobility and accurate fire during movement were not luxuries, but essential capabilities for modern armor. The Leopard 1, entering service in 1965, featured advanced two-axis stabilization, allowing accurate engagement while moving at high speed. The design philosophy emphasized reliability, maintainability, and combat effectiveness over pure specifications, reflecting lessons German engineers had learned from studying American equipment during and after World War II. For American tank development, the stabilizer represented validation of the design philosophy that had guided Sherman production. The M26 Pershing heavy tank, entering service in the final months of World War II, featured improved stabilization systems. The M46, M47, and M48 tanks of the early Cold War period incorporated increasingly sophisticated stabilizers. The M60 series tanks featured fully integrated fire control systems where stabilization worked in concert with range-finding and ballistic computers. By the time the M1 Abrams entered service in 1980, stabilization was so fundamental to tank design that discussing it separately from other fire control systems made no technical sense. Modern tanks feature integrated fire control architectures where stabilization, range-finding, target tracking, ballistic calculation, and automatic gun laying function as unified systems controlled by digital computers. The principle that began with a Westinghouse gyroscope and hydraulic servo system in a World War II, Sherman had evolved into fire control capabilities that permit modern tanks to engage multiple targets accurately while moving at high speed across broken terrain. The tactical advantage that troubled German observers at Kummersdorf in 1944 became baseline capability for all competent military forces. The story of the Sherman stabilizer illustrates how tactical problems, engineering solutions, and industrial capacity interact in modern warfare. Identifying problems is relatively straightforward. Developing solutions requires engineering skill, but remains achievable for technically competent nations. Translating solutions into reliable production hardware at scale, while simultaneously fighting a global war, requires industrial maturity and organizational capability that few nations possess. The United States demonstrated this capability repeatedly during World War II, producing sophisticated weapons in overwhelming quantities, while maintaining quality and reliability. The gyrostabilizer was one example among many, including proximity fuses, advanced radar systems, high-octane aviation fuel, and countless other technologies that provided tactical advantages through successful translation of engineering knowledge into production reality. Germany possessed brilliant scientists and talented engineers who understood these technologies theoretically, but German industry lacked the capacity to replicate American production methods given resource constraints, strategic bombing, and the accumulated strain of fighting a multi-front war against better-resourced opponents. Understanding problems and developing solutions proved insufficient without the industrial capacity to implement solutions at scale. The captured Sherman at Kummersdorf forced German technical officers to confront this uncomfortable reality. The stabilizer was not theoretical technology or laboratory curiosity. It was production reality installed in thousands of enemy tanks, providing tactical advantages German crews faced in combat daily. German engineers could analyze it, document it, and understand it completely. What they could not do was replicate it in German tanks within any time frame that would influence the war's outcome. This recognition, documented in technical reports filed during autumn 1944, came far too late to matter strategically. Germany had already lost the industrial war by mid-1943, when American production reached full capacity and Soviet industry relocated beyond German reach. The remaining 2 years of fighting determined not whether Germany would lose, but how completely and at what cost in lives and destruction. For the German officers who tested the Sherman stabilizer and filed honest reports about its capabilities, professional competence required acknowledging enemy advantages, even when doing so confirmed that their own side faced insurmountable disadvantages. The admission that the stabilizer made Panzers obsolete in specific tactical circumstances was not defeatism but realistic assessment of technical facts that could not be altered through ideology or wishful thinking. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now, and don't forget to subscribe.